All right. Good afternoon, everybody. So we're talking about storage duration in C. So to introduce the next type of storage duration in C, I'm going to go back to Java very briefly. So here's an example of a class that uses a list as one of its fields. Right now, in this particular class, so the constructor for this class makes a new list, right, and assigns that list to our field up here. Okay. So in Java, when you write new, you are basically you are asking for memory that can store a new object. When you use new in Java, it's always paired with a constructor call. And so this combination of new plus the constructor call causes the Java runtime to allocate memory for an object and then initialize the object. In Java, that object persists until it's no longer needed, right? And so the virtual machine figures out how long is this object needed for, and then takes up the and then removes the object from memory when it decides it's no longer needed. Right? And so what that means in Java is that the that object there called stack persists across calls to different methods, right? So it's made in the constructor, right? That same stack is still alive when you call size, right? That same stack is still alive when you call push and pop and so on and so on and so forth, right? If someone else creates another class and they make a stack, right? Whatever list was created when the stack was created, that list survives as long as it's needed for. All right, so in C, we have something called allocated storage duration. And so in allocated storage duration, the programmer is under control of the lifetime of the object. Now, the problem is the programmer is solely responsible for the lifetime of the object, and that means the programmer is responsible for allocating memory for the object, using the object, and then removing or releasing the memory that's used by the object when they're done. Right? If you forget to release the memory when you're done, right, that object never goes away. Whatever resources it's occupying never gets released back to the system. Right? And so if you repeatedly do this over and over and over again, you can run out of resources. Right? So for example, you can run out of memory if you have lots of objects lying around that are no longer needed. Right. Okay, so when you want to do this in C, when you want allocated storage duration in C, the programmer is responsible for requesting memory for the object. Right? So we call that dynamic memory allocation. Right? There's no constructors in C, so the programmer is responsible for initializing the value of the object. Right? Once the value is initialized, it can be safely used. Then you can use the object. Right? When you're done, and so when you realize that you no longer need that object, the programmer must release the resources used by that object. Right? So you might ask yourself, so when on earth do I need to do this sort of thing? So you need to do this sort of thing when the object that you're creating needs to persist across calls to different functions. So if you, in this particular situation, which is very common, you have to do one of two things. Right? You either have to use static storage duration, right? So remember, static storage duration, the lifetime of the object is the entire lifetime of the program, right? So you never worry about having to You never worry that the object is no longer there, right? You don't have to worry about its cleanup or its initialization. Sorry, you might have to worry about its initialization. You don't have to worry about cleaning up after it because it's going to get cleaned up when the program stops, right? Or you have to use allocated storage duration. Okay, so static storage duration is not suitable for most things, right? So for example, if your program needs to create objects during the lifetime of the program, and you don't know which objects need to be created, you can't use static storage duration, right? Static storage duration, you need the variables present at the beginning of the program. So if you're implementing a data structure, like a list or something, or a stack or something else, right, where you need to dynamically store and release elements, you can't use static storage duration in that case, or it's not practical to use static storage duration. Right. Okay, so the almost always the first example that you run into as a new C programmer where you fall into the trap of not using allocated storage duration is when you try to write a function that returns an array of some kind. Right. So here's a function called int_array. It takes in an unsigned value representing the length of the array to create. Right. So in C, there are no zero length arrays. Right? So you're not allowed to make the standard says that if you try to make a zero length array, that the result is undefined. Right? So here I check is the length that's passed in, is it 0? Size type is unsigned, right? So you don't have to worry about negative values. So if the length is 0, I'm going to set the length to 1. I'm going to now create a little array using the syntax that I showed you a couple of lectures ago, right? So remember that array there has automatic storage duration, right? It's a variable that's declared inside of a block, right? So the lifetime of ARR starts here, right? The lifetime of ARR ends there, right? So whenever the function returns, ARR is gone, right? Or in principle, it's gone, right? And so what does this function do? Well, it makes a little array, then it tries to return the array. Notice the return type up here is funny. We'll talk about this a little later, right? But it looks like it returns the array. Right? That function down there the main function here calls the method, calls the function. Stores the return type again in a funny looking variable. Don't worry about the funny looking variable right now. We'll explain what that means in a little while, right? And then it tries to use the returned array right there, right? So it tries to print out the first element. And so what happens when you run this program? Number one, you get a warning, right? So it warns you, function is returning the address of a local variable, right? So the compiler is trying to warn you, hey, look, this thing here, right? It doesn't exist after this function returns, right? But you're returning you're returning that object anyway, right? So call the function, right? Array gets made, right? Array gets destroyed. Now you try to use the array and things blow up on you, right? In this case, it does blow up. When it ran, we ended up with an error, which is what this is complaining about, right? Exited with exit code -11. So something bad happened, right? And in particular, nothing got printed out. So obviously printing this thing didn't work. Right. Okay, so that example fails because the array that was created in the function has automatic storage duration, right? It's born when the block, its lifetime starts at the point of declaration, and it ends at the end of the block that it was declared in. Okay, so in this particular example, you can't return an array. You can't write a function that returns an array in that way. You have to do something else, right? And that something else is described in that notebook there, which we won't get to probably for a week or so, right? And so, but what you need to do is you need to create a variable whose lifetime is under the control of the programmer, right? You need to use dynamic memory allocation in this particular case. So we'll talk about that in a week or so. All right, so now you know about all the types of storage duration in C, right? The important ones are automatic storage duration, for our purposes anyway, it's automatic storage duration, right? Those are basically local variables that are declared inside of functions, right? And later on, allocated storage duration will become important. I don't think any of the code that I ask you to write ever uses static storage duration, right? But you should know about it anyway. And thread storage duration is not relevant to this course. All right, so the next notebook is the declarations notebook. Right, so we've talked about scope and lifetime. Now we're here. A lot of this will be reviewed because you're from you have already learned Java. Right? So in C, a declaration means that you are introducing a name into the program. Right. So when you declare a variable, you say a variable of this name now exists. Right. So basically, a declaration simply states that some name exists. Right. In C, the compiler needs to know a name exists before you try to use it. Right. If you try to use a variable before you declare it, that doesn't work. If you try to use a function before you try to declare it, that doesn't work either. Right. The compiler will refuse to compile your program. Right. So to make variables work more or less the same way as they do in Java. Right. Every variable has a type. Right. So int x says that there's a variable called x whose type is int. Right. Double y says there's a variable called y whose type is double. You can declare multiple variables of the same type on the same line. You just separate the names with a comma. Right. When you declare a variable, you get memory for the variable. Right. So int x actually allocates memory for that variable x. Right. That memory can store an int. Right. Double y allocates memory for the variable y. That memory can store a double value. Right. In C, the values are not initialized. Right. Wherever that memory came from, that's the value that you get. It might be 0. It could be something else. Right. So here, x and y, they are variables. There is an int called x. There is a double called y. You don't know what their values are. Right. Similarly, there are variables a, b, and c. They are ints. You don't know what their values are. If you try to print them, what do we get? I have no idea. Oh, you don't get 0 in this case. Right, you get some gibberish, right? And that's exactly what you should expect. If you declare a variable in C, you almost always want to initialize it when you declare it. Right. So C uses the term definition to describe declaration plus initialization of a variable. Right. So there, that defines x to be an int whose value is 1. Right. That defines y to be a double whose value is -1, right? And similarly, this defines variables a, b, and c whose values are -5, 3, and 5, right? This works the way you expect it to, right? It actually prints out those values, right? So declaration, right? Definition, which simply means declaration plus initialization. All right, C's got this thing called const. So you can modify a variable with the callifar const. It's similar to, but it's not exactly the same as final in Java, right? So const indicates that a variable is read only. So const x equals 1 says that x is a variable whose type is const int, right, and whose value is 1. Const int y says that there is a variable called y whose type is const int, and its value is indeterminate. You don't know what it is, right? The const means that the variable is read only, so you cannot assign to it after it's been declared. If you need to give it a value, it has to be defined, right? In other words, you have to declare it and initialize it all in one shot. Right? So this won't compile, right? Error, right? Assignment of a read-only variable y. So that program doesn't work, right? If you get rid of that line, so commenting it out, it will compile and it will run, right? You get 1 and you get some random value, in this case, 21,932. You run it again, you'll probably get something else. Yes, right? And again, something else, right? And so on and so on and so forth, right? So const means the variable is read-only. The const becomes part of the type, right? So the type of x is const int, right? The type of y is also a const int. Functions can also be declared in Java, right? So remember, the declaration simply says the thing exists. So I can declare a function like that, which simply says the function max2 exists. It returns a double, and it has two parameters of type double. And that's all that it says, right? Once you've declared that something exists, you can use it in your compilation unit, right? So in your source code, in your source code file. Right. So if I write this somewhere in my source code file, after this point, I can now call the function max2. It doesn't actually have to be defined in that particular source code file. Right. So I've got no definition of max2. So I have a little program here called uses max2. Right. It declares the function max2. It defines the function max3. Right. So max3 actually has an implementation. Right. Max3 uses max2 to compute the max of x, y, and z. Right. You simply compute the max of x and y, you get the result, and then you compute the max of that value in z, and that's the max value. Right. And there's a main function, sorry, that actually calls max3. Right. So on its own, max2, this file here, right? So that file that I'm showing you there, that does not constitute an entire C program, right? Why doesn't it constitute an entire C program? Because the definition of max2 is missing, right? So this is an incomplete C program. Somewhere there has to be a definition of max2. However, you can compile this file, no problem, right? So this is uses max2. So I can go into, well, you got too many windows open, sorry. Not this one, right? So there's uses max2, right? I can compile this. I can't compile it into a runnable program, right? So if I try to do GCC uses max2 like that, right? It'll complain, right? The compiler complains and says, hey, I don't know what max2 means, right? So that doesn't work. But you can compile this into what's called an object file. So GCC -C, right? So compile, but don't link. So don't create the final complete program, right? But that works just fine, right? Why does it work? Because the compiler, oops, sorry, uses max2.c, right? Right? Why does this actually compile? Right? Because the compiler knows what max2 is supposed to look like, right? It's called max2. It takes in two doubles, returns a double, right? And so when it compiles your program, it checks, right? Does this make sense? The answer is yes, it makes sense, right? Given that declaration of max2, right? It can't create the complete program because it doesn't know what max2 actually does, right? Or how it's defined. But that will compile, right? So go ahead and do that, compile it like that. So to complete the program, somewhere you have to define max2, right? And so we can create a separate file called max2.c and put the definition of max2 there. So over back here. Right. Right. Whoa, sorry. That, right. So there's my definition of max2, right? It's in a separate source code file. I can compile this. Right? I can't create a complete program, right? There's no main function. So I can't, if I try to do GCC max2.c, it's going to complain there's no main, right? But I can certainly compile and not produce a runnable program. So -C, right? Compile to object code, but don't try to link. And that works just fine. If you look in the directory, you'll see there's a max2.o, right? So there's an object file which was created from there. There's uses max2.o, which is the object file that was created when I compiled uses max2. And now I can compile all of this into a complete program, right? So the way you do that is you specify what are your two object files. Right? So like that. And that spits out a.out. If I run a.out, it actually runs, and it tells you the max of 5.2 minus 1.3 and 4.9 is in fact 5.2. Right. You can also compile the program if you want to give it a name. So max2.o uses.o So minus O uses max2. I'm going to call it complete. Right there. Right. So now you can run that program there. All right. So the notebook tells you, shows you a couple of ways in which you can actually compile this into a complete program. All right. So this seems a bit odd, right? So in order to compile that program, you need to know that uses max2.c exists, right? You have to have access to the source code. You have to be able to see inside of it to see what the functions actually are, right? And so declaring functions defined in another file is error prone, right? So splitting up your program and throwing functions into other files is error prone if you are relying on knowing that certain functions live in certain files, right? More generally, you might not have access to the source code being provided by other people, right? You might just get a compiled version of their source code. So you might get the .o version of their source code, right? You don't have access to their source code. You don't know what's in it, right? And so, so this seems like a bit of an odd way to do things, right? So given a program that's been split up like this, what a lot of new programmers will do is they will say, hey, I know what include does. Include takes the contents of a file and drops it into my program. So why don't I include max2.c into my program bad uses max2.c, right? Don't do this, right? The rule that you should remember is never include another source code file into your program, right? So never include a .c file into your code. You might come across some very old software frameworks where you have to do this, right? But in general, don't do this unless you absolutely have to. Right? Okay, so if you write this program, right, it turns out you can in fact successfully compile this thing, right? So I just told you don't do this, but if you type that in to your command line, this in fact works. Right, and this is what happens on a lot of assignments done by students in this course, right? I'll give you a bunch of source code files, right, and they'll just include the C source code file from that contains the function that they want to use, right? Don't do that. I'll show you what you should do in just a second. So bad, that, right, and that seems to work, right? Solves my problem. It runs. And so a lot of new programmers will actually do this sort of thing, right? There's a problem though, right? So at first glance, this appears to work. Solves our problem of having a function defined in a different file, right? However, if you try to compile your program in a different way, suddenly everything breaks, right? So remember, all of my functions are defined in two files, right? Bad uses max2.c and max2.c. So if I try to compile my program like that, UCC max2 and uses bad .c and save that as right. Oh, hey, now we got a compiler error, or more precisely, right? LD is the linker. We have a linker error, right? And so if you stop for a minute and look at what it's complaining about, right? It says there are multiple definitions of max2. Right? And so in other words, you created a program that has two things called max2. And now the linker can't decide which one do you actually mean to use, right? And so why are there two versions of max2? Right? Because when you include max2.c in your file here, right, that drops the definition of max2.c into this file, right? So when you compile that file, max2.c is defined there, right? Now you're also compiling max2.c, which contains max2, right? So you now have a second version of max2, the function max2, in that in the compilation unit for that file, right? When you try to stitch those two things together, now you've got two definitions of max2, right? And the linker complains. So that's not the solution, right? So those two, if you try to compile things separately and then put everything together after the fact, that also doesn't work, right? So the linker error occurs because max2 has been defined twice, right? In C, the name of all functions having what's called external linkage must be unique across the entire program, right? All functions have external linkage unless they're marked as being static. So max2 has external linkage. That name has to be unique in the entire program, right? And so this happens all of the time when you start to build larger C programs, right? You've got functions defined in multiple different source code files, right? And you want to call functions that are defined somewhere else. How do you do that? The answer is you put the declarations of your functions in one file, and then you have those definitions in another file. In C, the declarations go into a header file, right? And by most C programmers will save their header files in a file that ends in .h, right? So for max2, we write the following. Right. So we've got this funny if end def, which I'll explain in a second, and a define, which I'll explain in a second. Right. We put the declaration of max2 here. Right. Now in the program, any program that wants to use max2 includes the header file, right? Not the source code file. Right. The header file serves the purpose of saying this function exists, but it's not defined. Right. Max2.c actually contains the definition, right? Notice in max2.c, you include the header file, right? Including the header file says that function exists, right? And here's its definition, right? Now in any other file that wants to use max2, you include the header file, right? What does that do? It says, hey, this function exists, right? But the definition's not there. So that when you go to link your program together, you don't run into the problem where you've got multiple definitions of the same function, right? Okay, so let's try that. And let me just find the file that actually uses max2, also uses max2. Okay, so, right, so here's the version of uses max2 that includes the header file. So let's compile that. So also, oh, sorry, GCC minus C also uses max2, right? Compiles no problem. Now let's link everything together. Right, so there's the object file corresponding to the source code file I just compiled. Right, there's the object file corresponding to max2. Right, put that all together into one program. Right. Oh, also uses no such file minus, oh, sorry. And so, right, everything compiles and links. And if I can type properly, the program also runs. Right. Okay, so the idea is if your program consists of multiple source code files, right, create a header file for all of your source code files. In the header file, place the declarations of the functions that are defined in each source code file. Right. Now, your header file should always start with what's called an include guard, right? And the include guard, all it does is it defines a unique identifier for your header file. Right, so back here, right, the preprocessor command define simply creates a preprocessor variable called max2_h. Right, by default, this is most programmers write these in all uppercase. Right, so there's some symbol or name called max2_.h. You can give it a value if you want to. You just put the value after max2.h with a space, right? So that name now exists, right? And now everything, and now all of that, and then you have the declaration of your function. Right. Okay, So the if-ndef is a preprocessor directive that tells where the preprocessor says, looks at this directive, and it says, if this name does not exist, right, do everything in between the if-ndef and the end-if, right? So if you include the header file once in your program, right, max2_h does not exist the first time you include it, right? So what happens? The preprocessor defines the symbol max2_h, right? Now you get your declaration of your function, right? The second time you include the header file in your program, right, the preprocessor says, oh, hey, this thing already exists, so I'm just going to skip over to the end if, right? And now it does not re-declare the function max2, right? So the include guard prevents your functions from being redeclared over and over and over again. So the you can read about the explanation here in the notebook if you need a reminder what it's doing, right? Okay, so the header file. So the reason you want to do this is if your header file ends up being included into the same compilation unit multiple times, right? The preprocessor won't include it over and over and over again. And you might say, well, how can you include a header file over and over and over again, right? And it turns out it happens very easily, right? So in a large program, your files will include many header files, right? Some of those header files might include other header files, right? And so you can easily end up including the same header file over and over and over and over again, right? And so the include guard simply prevents that from happening. All right, any questions about declarations in a C program, right? Declaration simply says this name exists. Okay, we are actually on to the next notebook now, which is statements. Right, so we've done declarations, now we're doing statements. This is also largely review for all of you, or should be anyway, because the statements in C are more or less the same as the statements in Java. Right, so assignment, well, we all know how to do assignment, right? Variable equals some value, right? So one of the things you have to be careful about in C, right? So when you start to work with arrays, right, so here I have an array variable called X, right? X is an array of int, right? I've got an array variable called Y, right? Y is an array of int. In C, you cannot assign to an array variable, right? You can initialize it, right? But you can't, you can initialize it. So initialization, remember, happens at the point of declaration, right? But you can never assign to an array variable, right? That will never work. One of the reasons this is important is because in C, strings are just arrays of car. So you can't make an array of car for a string and then reassign to the string, right? Which is a natural thing to do in languages like Python and Java. Right, so str1 is an array of car. It holds the string hello. Right, str2, another array of car. It holds the string bye. Right, you cannot make str1. You cannot assign the array bye \0 to the array str1. Right, that will never work. If you try it, right, you get all sorts of compiler warnings. Where is the initializer? Oh, well, you get all sorts of you have all sorts of compiler warnings here, warnings and errors. Right. All right, function calls. Function calls work like method calls in Java or function calls in Python. Right. Call the function. Pass in the arguments, make sure the arguments, the types of the arguments are compatible with the parameter types that the function actually declares. If it returns something, you can store the result in a variable, right? So that's how you call sine, that's how you call cosine in C, right? Those functions are defined in the header file, declared, in the header file math.h, right? So include the header file. Somewhat surprisingly, there is no definition of pi in C, or at least not in standard C, right? So you'll have to define it yourself. This is how you use the preprocessor to define and assign a value. Right? So hashtag define says ask the preprocessor to define the value mpi and give it the value that. Right? All that happens is that when the preprocessor reads your program, everywhere it sees mpi, it substitutes 3.14159 blah 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 blah. Right? So in your after the preprocessor is done finishing, the thing I have highlighted there will actually be 3.14159. Right? That not surprisingly prints. Whoa, what's going on? Oh, hey, what is happening here? Undeclared. Oh, this one's. Sorry, this one's not going to work. Is there a warning here? Hang on just a second here. There's no warning here. You need to link to the math library here, I think, which is the problem. Expected declaration specimen. Or did I do something wrong? No, I did everything okay, right? %f. Sorry, just let me. I'm just trying to just make sure that I didn't screw anything up. It looks okay. I think it's complaining that I think the complaint here is that it's not linking to the math library. All right, but anyway, so the calling a function looks like calling a function in Python or calling a method in Java. Okay, your statements in C. So you have all the same control structures that you have in Java, right? If statements look exactly like if statements in Java, right? If condition in round brackets, right? Else if condition in round brackets, right? Else no condition, right? So that works exactly the same as in Java. There's a switch statement in C, works the same way as a switch statement in Java, right? If you want to know how to use it, just click on that link there. I won't ask you to do it. Right. Loops in C are the same as loops as in Java. Right. So a while loop in C looks exactly the same as a while loop in Java. Right. While that condition is true, the loop body runs. Right. So this loop, does this one work? Oh, wait. I wonder what's going on here. Something is, my Jupyter is not happy right now. I wonder what's going on. So I don't want to shut down Jupyter and restart it. Well, let me shut down Jupyter and restart it. Sorry. Well, we can try that. But I have a feeling that's not going to work. I haven't rebooted my computer. So this has been running on my computer since before reading week. So I'm not totally surprised that it's barfing. Let's see what happens. Oh, kernel's died. So there's the problem. Let's see. Okay. Is this going to work? No, it's still barfing. All right. Okay, bear with me while I restart Jupyter. Talk amongst yourselves for a few moments. All right, so there's something going on. Okay. Okay. So we are in CBART. Okay, is this working? Oh, hey, that's not working. Alrighty. Anybody have a Jupyter Notebook open and running? Yes. Maybe. Although that would have been a change compared to previously. Is that really what the problem is? No, it's not. It's still varping. Oh yeah, see, that's weird. So something funny's going on. Because I did test all the notebooks before I released them. So something weird's going on. Let me look into it and I will try to resolve it after the lecture. But all of these code cells should run because all of the C code here is correct. So I'll try to figure out what's going on after the lecture. I wonder what's happening here. Somebody else showed me a weird thing happening on their computer. So I wonder if something has changed in Jupyter. All right, anyway, switch statement to while loops, do while. So I don't normally show you these in 124. If you took 124 with me, there is also a do while loop, right? And so in both C and Java. So in a do while loop, the condition is at the end, right? So in other words, the body of the function of the loop always runs at least once because the condition is not tested until after the loop body executes, right? So this prints out the value I and increments the value I until the value of I is great until the value of I reaches the stopping value, right? Finally, for loops. Right, so for loops in C, there is no enhanced or do or for each loop in C. You only have the counting style loop, right? So if you're going to write a loop in for loop in C, it always looks something like that, right? Create your loop variable, initialize it, right? That's your loop termination. There's your loop termination condition, right? The loop runs as long as that condition is true, right? At the end of every loop iteration, that's your loop update statement, right? So the value of I goes up by 1 each time. The break statement will break you out of a loop in in C and in Java, right? So this loop runs forever, right? While 1 is effectively the same as while true in C, right? And so this loop runs until I is greater than 5, right? Hopefully you're updating the variable I somewhere in the loop, otherwise this thing's going to run forever. Right. Continue, there's also a continue in Java, right? Continue will skip over the rest of the iteration, over the rest of the current loop iteration. Right. So this loop runs I equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. When it gets to the loop iteration where I is equal to 5, it skips over the rest of the loop. Right. So in other words, it does not print out 5. Right. It just goes to the next iteration, 6. And so now this will print out 0, 1, 2, 3, 4, 6, 7, 8, 9. Right. So if you need a reminder of how the basic statements work in Java and in C, that notebook is there for you. Okay, finally the integers. So there is some, oh, sorry. You might wonder why there's an integer notebook. And that's because we actually explained to you how unsigned and signed integers are represented on your computer. So the integer types in C work more or less the way they work in Java. There are some big differences, though, between the two languages. So number one, technically the language does not say how your integer values are represented on your computer, right? So the language doesn't say, for example, the signed numbers on your computer are represented using something called 2's complement, right? It simply says you've got signed integers. This was supposed to change in the most recent version of the C language standard. I don't know if it has. Right. The implication of this is that overflow in C may not happen or may not work the exact same way that overflow in Java happens. However, on any desktop computer that you'd run C on, it's going to work the same way. The other big difference between C and Java is that the C standard doesn't say how many bits are in each type. Right, your int might be 32 bits, it might be 16 bits, it might be 9, right, or something else, depending on the computer that you're running it on. There are more types of integers in C, right? You have the signed and the unsigned types. And furthermore, C is more permissive than Java when you're converting between different types. Right, and so there's your table of all the integer types, right? There's a lot of them. Right, bool is an integer type, even though it doesn't really behave like one. Right, char is an integer type, even though you normally don't use it as an integer type. Right, there's short, there's int, there's long. There's also a long in C. There is no long in Java. Right, notice that the size of all of these things, the specification is very vague. Right, the specification only says what is the minimum number of bits in each type. It doesn't say the actual number of bits. The standard does say what the order of these how these things are ordered by their size. Right, so a car, its size is always 1. Right, size of car is always 1. Right, it's usually 8 bits. Right, short is supposed to be at least the same size as car. Int is at least the same size as short. Long is at least the same size as int, and long is at least the same size as long, but the actual size isn't specified. Bool we talked about earlier. Bool is just true and false values. Right? If you actually want to use the name bool, you have to include that header file. Right? Because it's a late addition to the language. It's a surprisingly late addition to the language. Right? The language was kicking around for 20 years before they introduced a logical type. Right, char we know about already, right? Char is your type that you use for representing characters. Right. Now, what about the integers? Okay, so we have unsigned and signed types in unsigned and signed integer types in C. So the unsigned types are never negative. Right? So their minimum value is 0. They go up to some maximum positive value. Right? There's a maximum positive value because the amount of memory is finite. They have the simplest binary representation, right? So an unsigned number, if you were to write it out in binary, right? So zeros and ones, you can the decimal value is obtained by multiplying each one of these digits by some power of 2, right? Now you can write this in 2 different ways. I'm always going to write it the same way. So for us, the leftmost bit is always raised to the highest power, right? The rightmost bit is always raised to the power 0, right? Going from right to left, you increase the power by 1, right? You can write this the other way. So you could have this be 2 to the 0 and this be 2 to the 7, for example, right? But I'm always going to write it this way, okay? So that 8-bit number there, 011011011, right? Its decimal value, you just take the bit, so 0, and multiply it by the corresponding power of 2. Right, so that number there is equal to 0 times 2 to the 7 plus 1 times 2 to the 6 plus 1 times 2 to the 5, and so on and so on and so on. Right, you multiply that all out, and hopefully I told yes, it's equal to 107. Right, so the power of 2 is called the multiplier. Right, the zeros and ones are your bits. The numeric value is just the bit times the multiplier. Compute the sum to get the final decimal value. Right. The bit with the highest multiplier is called the most significant bit. Right. So that bit there, that 0 corresponding to the power 2 to the 7 is the most significant bit. It's called that because it contributes the most to the overall magnitude of the number. Right. Not surprisingly, the bit over here is the least significant bit, right? It's called the least significant bit because its value contributes the least to the overall number, right? So for us, the most significant bit's always on the left. The least significant bit's always on the right, right? So it's common to write them from left to right, starting from the most significant bit to the least, right? But you don't have to. Okay, so what is the minimum unsigned value, right? So what is its bit representation, right? Well, it's just the unsigned number it's just the binary value whose digits are all 0, right? 0 times the power, 0 times the power, right? So that's equal to 0. The maximum value, its binary representation is all ones, right? So 1 times 2 to some power plus 1 times 2 to some power and so on and so on and so forth. So for an 8-bit number, right? The smallest unsigned value is 0. The largest unsigned value is 255, right? If you have n bits in your number, right? And if you remember your math 201 or whatever, right? You can prove by induction that the value of the maximum value of an unbit unsigned binary number is 2 to the n minus 1, right? So that's how the unsigned numbers work. Now the signed numbers use something called 2's complement, and I'm out of time, so we'll talk about that in the next class.